Alright, what's up guys? This is the periodic table review. Here I'm going to go over a lot of the content, some of the main points, go a little bit more in depth on some explanations and such. So here, if you were here on class on Friday, I gave you like pretty much a guided sort of review notes here, or a bunch of guided questioning to help you guys remember much of the main concepts that you're expected to know going from Monday's test. Alright, so let's begin. And so let's start with looking at the periodic table. So here you should be having your reference table, your own periodic table right next to you to help you through this. And so here we should look at the periodic table, and it's being arranged in what kind of order for atomic number? Is it going up or is it going down as we go across? Well, here it's going to be going up. So it's going in order of increasing atomic number. Increasing atomic number. Alright, there, I drew a little reference periodic table for you guys as reference. And so if you notice from here, we start with number 1, that's hydrogen. And going all the way across here, we just go up in increasing number, going from 1 all the way to 118. Alright, and now let's talk about the next point, the vertical columns. So these are the guys that go up and down. Down here, down here, down here, so on and so forth. Those are called groups. So those vertical columns are called groups, but if you're going across these horizontal rows, these are called periods. Sorry. Now, each of these elements that are grouped together this way share something similar between them. And so let's talk about the ones in the same column, the ones in the same group going down from top to bottom. They share the same number of valence electrons. Valence electrons, and from there they also share the same chemical properties. So the number of valence electrons eventually moving forward to later units talks a lot about how these elements are going to bond with each other. And when they bond with each other, there's something special like chemical properties, how they react with each other that way. So there's special chemical properties that come from the way they bond, the way they react, the way how many valence electrons they have. So that's for moving forward. Now, what do elements in the same row share? So those in the same horizontal row, same period, they have same number of electron shells. So the same number of energy levels. That's supposed to be 2 words. Electron shells. Okay. So I think I'm going to start doing this. I'm just going to shrink these slides so that I have a lot of writing space here for my explanations, especially for this type. Now let's talk about the types of elements. So I'm going to once again draw my little fake periodic table because I can't upload one to this video at the moment. Looks something like that. And here this periodic table is broken down into 3 main types. The metals. We also have the nonmetals. And the metalloids. And it's important for us to know where to find them. So let's start with the metals. All of the metals are over here. Okay. So they're mostly towards the left side. Now the nonmetals. The nonmetals, well actually the metal, this is a nonmetal, my mistake. Those are the nonmetals, they're all the way to the right side. Now the metalloids. These metalloids are like an in-between of both metals and nonmetals. So they're in this weird region right here. Now the way to distinguish that, there is going to be this bold staircase right here. And it's on your reference table. So the ones that touch the bold staircase are considered metalloids. So they're on the right side touching both staircase. Okay. Now, based on this coloration, you can tell what the periodic table is comprised mostly of, and that's metals. The majority of all the elements here are made of metals. Now, we need to also know some of the properties of each type. You're expected to know this. So let's start with metals. That one's easy to remember. So let's talk about metals. Let me do it in this space here. So metals. They have luster, so they're shiny. They are also malleable. They are also ductile, so that means you could make it into wires. So malleable meaning you could hammer it into shape, and ductile meaning you could pull it out into wires. So think about the electrical wires you use, or even the wire fencing. So that's an example of metals that are ductile. They're also good conductors. Good conductors of electricity and heat. So those are some of the main characteristics of metals. Now, nonmetals. Let's talk about nonmetals. They're pretty much the opposite. They're lackluster. They're also brittle. That means they kind of crumble. They're also poor conductors of electricity and heat. And then there are metalloids there that have characteristics of both. So they're a mix of both. So the next thing we're going to talk about are group properties. So there are 5. There are 18 groups across the periodic table, 18 different columns. But there are 5 main categories, 5 main types that we have to know, and at least know their names. And so let's start with group 1. That means it's the one towards all the way to the left, group number 1. They're these guys right here. They are called the alkali metals. So these alkali metals, with the exception of hydrogen right here, they're all metals. Except hydrogen. They only have one valence electron. So if you look at their electron configuration at the bottom of each element box, you'll see that number 1 is the last number in that electron configuration pattern. So what are some other properties of them? They're metals, except hydrogen. They have high reactivity. That means they like to react. And they typically lose electrons to make cations. Alright. Another group that's very similar to them is group 2 right here. These are called the alkaline earth metals. Alkaline earth metals. Now, being group 2, they have 2 valence electrons. They are also metals. They also are pretty reactive. And they also make cations. So there are a lot of similarities with group 1, but there are also the slight distinction of having 2 valence electrons. Alright, now groups 3 through 12 over here. So this whole chunk right here. Let's color that in a lot. Sorry. These are called the transition metals. Wow, you can't even see that on the box. Transition metals. I hope you can read that. Let me pick a darker color. Alright, so let me finish coloring that in while I'm in the midst of finding a different color. You know what happened to me today? I ran over something today. No, I didn't run over an animal, guys. I ran over like this plastic, I don't know what you call it, this plastic piece of material, and it punctured a hole in my tire. So I had to get my tire fixed. No, not even fixed. I had to replace the tire. That was a waste of like almost an hour or 2 hours of my life today. It was a bummer. Oh well. At least it wasn't all 4 tires. That's a lot of money to get those replaced. But anyway, now I found a darker color. So let me write that over. Transition metals. Hope you could see that. Now, the number of valence electrons doesn't matter here. They kind of lose between 1 or 2 valence electrons. Some of them have more valence electrons. It doesn't really matter at this point. But the big thing about them, they're mostly metals. And they make pretty colors. Yay, pretty colors. So if you think back to the flame test lab we did, iron had a really bright orange. If you did copper, it was green. If you had cobalt, it was like blue. So those are examples of like transition metals in that group that make all these pretty colors. Next, we move on to group 17 right here. Okay, so these guys are called the halogens. I love the halogens. They have 7 valence electrons. They are very reactive. They're all nonmetals. They make anions. And there's one especially other important fact here also. I'm going to put an asterisk here. They are mostly diatomic. So when I say diatomic, let's think about the word. Di is the prefix meaning 2, and atomic meaning atoms, so 2 atoms. So an example of that would be fluorine. So fluorine exists as F2 in nature. So that means you take 2 fluorine atoms, and you got F2. That's a diatomic fluorine. So it's all about taking these 2 atoms of the same element, hence diatomic. Another one is like chlorine, iodine, bromine, etc. So there's a special phrase to remember about all the diatomic elements. So this phrase is for all of the diatomic elements, not just those in group 17. So Han, Col, Brif. Whatever other phrase you hear from the other chem teachers, ignore it. Use mine, Honkel Brif. I'm trying to take down Mr. Balance evil propaganda right here. Honkel Brif. So hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine. So all of these here are the diatomic elements. So that means they occur in nature as 2 atoms together of the same element, diatomic. Alright, so that's group 17, the halogens. And now let's go on to my favorite over in group 18. Guess what they're called? Let me pick a different color. Let's go with a light blue. Okay, that's pretty. Over here, including helium, these are called the noble gases. They have 8 valence electrons. They have 0, almost little, reactivity. Why? Because they're very stable. They're nonmetals. They're pretty much all gases. And they're the most noble of all the elements. They have reached enlightenment. They are stable. They're happy. Everybody wants to be them, the noble gases. Alright. Okay, now we go on to some of our trends here. And let's start with atomic radius. This is probably one of the trickiest trends here, I'll admit. Okay, so let's start with this. So let's talk about what is atomic radius. Well, that talks about the size of the atom. Well, mostly the radius of the atom, which relates to the size of the atom. what's important for us to see here is the trend that goes down the group and across the period. Because yes, as you go across the periodic table, you'll start to see that some things go up and some things go down. Now let's talk about going down the group this way. We're going to take group 1 as our example. So looking at hydrogen, lithium, sodium, and let's do potassium as well. So these 4 are different examples. So those in the same group have the same number of valence electrons, but as you go down, they're in different periods. So they have different number of electron shells. And let's start with hydrogen. Hydrogen only has 1 electron shell. Lithium has 2. Sodium has 3. 2 and 3. And then potassium has 4. Whoa. So as you notice, as you go down the group, going from hydrogen to lithium to sodium to potassium, you increase in size, because you're adding more and more electron shells, which increases the radius of the atom. Now, this is the trickier one, going across the period. And for this example, what we're going to use is period 2. And we're going to look at carbon, nitrogen, and oxygen as our example. So carbon, nitrogen, and oxygen here. So given that they're all in period 2, that means they all have a space of 2 electron shells. So 1, 2. 1, 2. And O is 1, 2. Okay. So I actually didn't draw this to how they're supposed to be according to the trend, but let's start with this idea that they have 2 electron shells as our base. So this is their base size. So I'm going to make a special note here. This is their base size. Now taking into account their nuclear charge, that means the charge inside the nucleus. We're looking at the number of protons each of them have. So carbon has 6, nitrogen has 7, and oxygen has 8. This is the number of protons that they have inside the nucleus. Okay, so let's see. So that means the stronger your nucleus is, the tighter it pulls on the shells. So think about a stronger magnet that's pulling in on the inside. So it causes your rings to come closer together. But notice how I'm going to decrease the size between the rings here. So going across, so look how between 6 plus and 8 plus, the distance, the gap between the rings start to decrease as you move across the period, because your nucleus gets stronger with more and more protons. They all have the same base size being in the same period. They have 2 rings each. But the gap between the rings starts to decrease in size because you have a stronger nucleus with more protons being added. So here, your size decreases as you go across the period because of nuclear charge. Okay, so they have the same base size with same number of electron shells, but the stronger your nucleus gets, the tighter it pulls it together, decreasing the gaps between these rings. Alright, electronegativity. So this talks about the strength of attraction for electrons. So strength of attraction for electrons. Now, which element here has the highest electronegativity? So I'm going to use this as our reference point. So fluorine here has our highest electronegativity of 4.0. So it's it's measured in a scale of 0.0 to 4.0 being the highest. So fluorine has the highest of 4.0. So this isn't exactly like you could take a measurement tool to measure it exactly. It's a scale relative to all the elements. So they rank all of these elements together from 0 to 4. Okay, so 4 being the highest, fluorine has the highest electronegativity. Now let's look at the trends across the period and down a group. So going across the period. So as you notice, as you go from left to right, you're getting closer to fluorine because over here on the left side, you have metals. Metals only have one valence electron. They need 7 more to be stable to reach 8. So that's a lot of electrons for them to gain, but it's also a lot of work. What they can also do is just lose their 1 electron. So something like lithium over here doesn't want to gain 7, it wants to lose its 1 electron. So lithium only has 1 valence electron. It's easier to lose that and be full with your valence shell. So they don't want to gain electrons. Fluorine, on the other hand, has 7 valence electrons. It just needs 1 more to fill its shell of 8. So that's why it wants so much electrons. It's so strong, that electronegativity, it really wants those electrons to fill its shell. So going across the period, you're going to increase in electronegativity because you're getting closer to fluorine as well. Now, as you're going down the group, let's compare fluorine to bromine. Let's see let's compare to iodine over here. There's chlorine and bromine over here. Let's compare it to iodine. So iodine, like fluorine, also has 7 valence electrons. However, you're also moving away from fluorine. So as you move down the group going away from fluorine, you're decreasing in electronegativity. Alright, now ionization energy kind of goes hand in hand with electronegativity. So ionization energy, on the other hand, is like an energy shield. It's basically how much energy needed to remove an electron. To remove a valence electron. So this is the energy needed to remove a valence electron. So this is an energy shield that protects the valence electrons for some of these elements here. Whereas electronegativity is an attraction, that means you're attacking other elements for their electrons. Ionization energy is an energy shield to protect your own electrons. So the higher that ionization energy is, the more you really want to keep your electrons. So high ionization energy leads to elements that are very greedy and want to keep their electrons. Okay, so which element has the highest ionization energy? That's helium. Helium's all the way over here. Now, if you notice this whole group, the noble gases, these guys are very full. These noble gases, they have their valence shells being full. So they're very stable. They don't want anyone touching them. So that's why they have the highest ionization energy. So noble gases have high values. They have high ionization energy values. They want to keep them. Trend across the period. So let's talk about that one. Going across the period. So let's take lithium as our example to compare to helium. So lithium only has 1 valence electron. Does it really want to keep that 1 electron? No. It really wants to give it up. So it's going to have a weak shield. So lithium has very low ionization energy. Now let's talk about fluorine also. This one has high ionization energy, and let's think about why. So fluorine's over here. Fluorine, just like helium, fluorine is very close to achieving that stable shell of 8 valence electrons. It has 7. So it'd rather keep all of its electrons and try to attack other elements for 1 more. So it doesn't want to lose any of those 7, otherwise it's going to work harder to get closer to 8. So that one has high ionization energy and wants to keep its electrons. Okay? So going across, you're increasing in ionization energy. Now going down the group, it decreases. And again, I want to use helium as a reference point. Helium has the highest ionization energy, so the further away you go from helium, you also decrease. But if you go closer to helium, you increase. So use helium as your reference point. And thankfully, helium and fluorine are in the same vicinity of each other. So ionization energy and electronegativity trends follow the same pattern. Alright, ionic radius here is not the same as atomic radius. That means we're talking about elements that become ions. So that means when you lose or gain electrons but still stay the same element, stay the same number of protons. So what kind of ion is formed when atoms lose electrons? So when you lose electrons, you become more positive. So let's think about the phrase that I use. Cations are positive. So these are cations. Cations are positive. Cats. Yes, I love cats. Alright. So how would losing electrons affect the size? So let's talk about sodium as our example. Sodium has an electron configuration of 281. So in order to bond with other elements, it wants to give up its electron. So it becomes a cation. So Na is over here just as a reference. It loses 1 electron to become 2,8. Now what do you notice here? 281, 3 electron shells. 2,8, 2 electron shells. So let's draw that out. 1, 2, 3. And then there's Na plus. There's just 1, 2. So cations in general are smaller. So over here, Na is bigger than Na plus. Now let's talk about the anions. Oh, well, I spoiled it already. What kind of ion is formed when you gain electrons? So you become more negative. Therefore, you're anions, because it looks like the word onions, and I don't like onions when they're raw. Looks like onions. Let's use a different color. Okay. So let's use a different element as our example here. So let's talk about fluorine. Fluorine's over here. Fluorine has an electron configuration of 2,7. Fluorine, when it gains an electron, becomes 2,8. So base-wise, they're still about the same size. But now that you have more electrons, you can also increase the gap between the rings. If you think back to atomic radius, where you decrease the size as you add more protons, here you're still keeping the same number of protons, but what you're adding on is more electrons. So all these electrons on the outside are going to push outward now, increasing the size. So as you add electrons, you become more fuller because these electrons are going to push outward. They're going to expand the gap between these rings now. So F here, F minus is bigger than F. So here it gets bigger. So this trend with ionic radius does not follow atomic radius, My key strategy here is to look at the electron configuration to help you figure out the sizes with the ionic radius, all right? And so that brings us to the end of our review video. Take a look at the practice exam. Definitely use this content to help you and guide you through the practice exam later on. All right, take care, guys.